In this situation, we have a roller coaster train being pulled up a hill. We're going to identify what we're given, the mass, the angle of the inclined surface, and that it's moving at a constant velocity of 1.6 meters per second. We also know the coefficient of friction. Now drawing a free body diagram for our situation. We've got an applied force pulling the train up the hill. We've got a weight, that's our field force, a normal force, and also a frictional force being applied. Now in part A, we want to calculate the frictional force. Mu times the normal. We know our mu value, but we're going to have to calculate our normal force. We have an equilibrium in the y direction. We need to calculate the components of the weight to be able to fill into that equation. Fgx and Fgy. Again, the weight is the hypotenuse of your right triangle, using a cosine to calculate the adjacent side, which is the y component, and then a sine to calculate the opposite side, which is the x component. Now we can fill that into our equilibrium in the y direction and solve down for the normal force. So the normal will be equal to Fgy. Putting that in for the normal into our friction equation, we can calculate the value of the frictional force. In part B, we want to calculate the value of the force applied to the train to pull it up the hill. X direction, so we're going to sum all the forces along the x direction, recognizing that we have an equilibrium. So force applied minus force of friction minus Fgx. Putting in our values, we can solve then for the value of the applied force. In part C, we need to recognize the motion has changed. Now the train is going down the hill. We have a displacement. The force has been removed, but we have the same coefficient of friction. So then, listing out what we know, recognize that you know the initial velocity. That's what it went up the hill at. You know delta x, and you want to calculate Vf. So now setting up our new free body diagram, we no longer have an applied force. However, we still have the weight, and we still have a frictional force and a normal force being applied. From our list of givens, we can tell that a motion equation is going to be useful. Vf squared equals Vi squared plus 2a delta x. However, we need the acceleration. We can go to Newton's second law along the incline in the x direction to be able to find that acceleration. Because this is a new angle of incline, we're going to need to go back through the trig and find our new Fgx and our new Fgy values. Now we can fill those values into our equation. We've got Fgx minus the force of friction is equal to ma. Friction is equal to mu times the normal. We're going to have to solve down for the normal force with the equilibrium in the y direction. It turns out to be equal to Fgy. Then we can fill that value into the equation along with the mass and solve down for that acceleration. Now with the acceleration value, we can fill back into our motion equation with our Vi value, our acceleration value, and our delta x value to be able to calculate the Vf. Ponder physics.